mercury barometer. So the gray silvery stuff is actually liquid mercury, Hg, and this is actually how a normal barometer works, where we have a closed end, and it's closed, a full vacuum, and then basically invert it in that open pan of liquid mercury, and then the more the pressure, the atmospheric pressure, than pressure of the atmosphere, the gas particles in the atmosphere, the higher up that liquid mercury goes into that glass tube. And so BAR stands for barometric pressure, otherwise known as atmospheric pressure. So that's just reading the pressure of the atmosphere. And we can actually use this liquid mercury barometer, we said, to kind of in a different way, not as like an atmospheric pressure gauge, but we can go ahead and take a liquid. The blue is the liquid in the syringe, and we're going to talk about volatility. It's a relatively volatile liquid, which means it's going to go from its liquid to its gaseous phase pretty good. And it's going to go ahead and be less dense. Mercury is more dense than it. It's going to rise here. And then we talked the other day about equilibrium, or basically those liquid particles. Some of those liquid particles are going to vaporize, and those gas particles are going to fill this tube. And if you compare the headspace there versus the headspace here, the addition of, or the depression of the liquid mercury in the tube is due to the pressure of the vapor that came from that blue liquid. Okay. And so actually you can go ahead and do a little subtraction. If you subtract that headspace, which was from the pressure of the atmosphere, the fact that it is now down to here, this change in volume, that's all due to that volatile liquid. So that's the pressure of the vapor. Let's see. I don't know what that's different there. Oh, we have side by side. Oh, this one is just showing that actually, to me, if I line these up, I have to go stand back there, but the pink lines look the same. And this is trying to show you that, see, this line and this line are the same. It's trying to show you that you have excess, you can have excess liquid, okay, that didn't go ahead and vaporize, excess liquid that didn't vaporize. You've still established an equilibrium vapor there. Okay? Now, if there was no liquid there, you'd be like, I think I might have run out of liquid to go ahead and evaporate. And there you might go ahead and see that it doesn't depress as much because you don't have as much liquid. Let's see what this one does. What's the difference between these two? Yeah, the two things, but the diameter is smaller. So this is one kind of phenomenon, kind of how a barometer works, but also how this liquid would establish a vapor at equilibrium. It doesn't matter about the diameter, okay? You're still going to get the same, the liquid mercury in your tube is going to react using similarly. So what's going on here? It's evaporating. Because we're going ahead and we're bumping up the temperature. We've got more evaporation, and so that gave you more gas particles, which depress the mercury on fiber. Yep. So there's no numbers here, nothing quantitative, just kind of qualitative look at these things. Oh, I forgot. All right. How likely is that liquid to go into its gaseous phase? So we kind of talked about if you can smell something, that means you are in your body is interacting with gas, with vapor particles that came from that object. So I brought this isopropyl alcohol, something that you can kind of just buy in the store. And the other day I had like some essential oils, and they're relatively volatile. So if it's relatively volatile, what can you expect? Like if I put my hand, will it be warm or cold under here? Cold, very good. It's kind of an evaporative cooling thing that you expect. So isopropyl alcohol is relatively volatile. Smell it. It's just like rubber smell. Okay.
So that means that the atmosphere, It's the candy and the atmosphere to break apart.
Yep, the energy can actually break off exactly. And isopropyl alcohol. Oh, this is the thing about propyl means 3, so we have 3 carbons. Okay, and these where the tick marks are actually just hydrogens. But my point here is isopropyl alcohol, what can it do? Starts with the letter H.
Hydrogen bond.
Hydrogen bond. It can hydrogen bond. But here I want to kind of point out that it can hydrogen bond, but it's relatively volatile. So hydrogen bond strong. Relatively volatile means that something's going to leak in it. So it happens. So, yes.
It's like this. In my biology class, we learned about bonds. Like, we went through chemistry at and she's saying that like covalent bonds, ionic bonds, and she said that hydrogen bonds were really weak. Is that like in comparison?
Yeah, we compare. Yeah. Hydrogen bonds are weak. Yeah, hydrogen bonds are weak compared to the covalent bonds, the chemical bonds. So it's all relative. Yeah. So like a water molecule, you can break the hydrogen bonds between the water molecules, but just regular, you can't break like the oxygen or hydrogen bond. So I think that's a good question. So I just want to throw that out there. So if something's relatively volatile, that means it will go into its gas phase kind of easier. So here's one for you. If we are comparing 2 liquids at the same temperature, and I think I'm going to draw little beakers up here. And we're going to measure their equilibrium vapor pressures. Now, just to kind of remind you how this works, here's my beakers. I have solution A. I'm going to put a watch glass over it. And right here in the headspace, that's my meter. Okay, it's going to measure pressure of these gas particles. And then here's my B. Okay, and it's going to be in it's going to be a dynamic equilibrium. I'm going to go ahead and cap it off. And here is my pressure gauge. It says the more volatile liquid will have the higher equilibrium vapor pressure. So this is T of A is equal to T of B, the same temperature. So I'm going to go for B. What do my more dots mean? Oops. More pressure. Yay, you got it. So this actually would be my pressure gauge here, and this could be my pressure gauge here. Go back. So all this is saying is, relatively speaking, if we're going to talk about volatility, we would say that B is more volatile than A. The volatile liquid will have a higher pressure. By the way, we have a slide coming up, I think, where it says equilibrium vapor pressure. That's a mouthful, but this is what it's describing. Sometimes it's just called EVP, equilibrium vapor pressure. And sometimes it's just called vapor pressure. Okay, so I have another scenario. I'm going to go ahead and draw my beakers down here. Call this, actually, yep. Darn it. Kind of have it's too much liquid, but that's okay. There's my watch glass to go ahead and seal it off. Now here, actually, notice that if you read the slide, we're trying to get them at the same temperature. Or sorry, we're trying to get them at the same equilibrium vapor pressure. I'll go ahead and use the same 2 liquids, A and B. Go ahead and cap it off. If they're the same equilibrium vapor pressure, I'm going to have, these are terrible drawings, but I hope you guys are translating them better. I'll go ahead and put 5, whatever I did, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll put 9, 3, 4, 5, 6, 7, 8, 9. I'll put 9 particles in each. So they're at the same equilibrium vapor pressures. And I'll kind of show the little dial at the same equilibrium vapor pressures. So I think that the thrust of this is saying, in this case, B is more volatile, right? And one of the things we're going to see is that if I cool it down, less is going to go into, there's going to be, the equilibrium pressure going to be less. So here, I'm going to see, say, temperature of B is going to have to be less than temperature of A. Why? Because it's more volatile. I'm at the same equilibrium vapor pressure. I can make that happen, but I have to cool down the one that's volatile. So the degree, the equilibrium vapor pressures, you're going to see some equilibrium vapor pressure curves here in a minute. Whatever pressure something exerts, equilibrium vapor pressure, is actually a function of the temperature. It's temperature dependent. And to me, if you go back to what we talked about in Gen Chem 1, this whole idea that temperature drives kind of your particle motion. Okay, all matter has motion in kinetic molecular theory. Okay, and as you cool something down, it slows down. Okay, so it's all consistent, I think. I like things that are consistent. So these are curves. These are all equilibrium vapor pressure curves for 4 different things. 1, 2, 3, 4. Notice what we have. We have temperature along the x-axis. And along the y-axis, we have what sort of pressure will that liquid exert when it's in its equilibrium. And not so surprising, as in general for all of them, as you increase the temperature, what happens to the equilibrium vapor pressures? They go up. As you increase the temperature, you increase the equilibrium vapor pressure. So, but here's the curve for ethyl ether. Ethyl ether has the ability to hydrogen bond, and it's actually got an extra oxygen in it. So, okay, ethyl alcohol, water, and ethylene glycol. So this one right up here, I had to look it up. This one right here is actually 760 millimeters of mercury, mmHg, otherwise known as 1 atmosphere. What's the importance of that? Maybe some of you know, but actually in this room, unless the barometric pressure is, and it's precipitating, usually our pressure is falling. But in general, the surface of the Earth, in general, runs about 760 millimeters per 1 atmosphere in general, plus or minus the weather fronts coming through. So that up there is actually atmospheric pressure. The other day, we said that when something boils, that means its equilibrium vapor pressure is equal to the pressure of the atmosphere. When something boils. Let's find water. This is the curve for water. Notice water will have this low equilibrium vapor pressure at these temperatures. Okay, so what are we at? So this room right now, you're talking maybe here-ish. This is about room temperature. So that means this is your equilibrium vapor pressure for water. Okay. Jack up the temperature, equilibrium vapor pressure increases. Jack the temperature up to 100 degrees Celsius. And what is your equilibrium vapor pressure of water? It's about, 760 millimeters of mercury, 1 atmosphere. See how that works?
So the other two, are they boiling at 80 degrees?
Yes, ma'am. Yep. She double checked. So this one, the yellow curve, the ethyl alcohol would boil at 80, and ethyl ether would boil at 35 or something. Yep. So, kind of putting these three, forget about this one for now, but which one has this, is the most volatile? The first one, yeah. Totally. Yep. This one is not very volatile at all, is it? And volatility is kind of telling you what's happening behind the scenes with regard to those intermolecular bonds that we've been talking about. The more volatile it is, less intermolecular bonds strength. It could be the number of bonds, could be the bond strength. the less volatile it is, the more intermolecular bonds, the stronger the bonds. So this is focusing just on water. So, yep, if we find 100 degrees Celsius, that's when our equilibrium vapor pressure is going to be, the pressure of the water vapor is going to be 1 atmosphere, 760 milliliters per minute. So I brought these in to kind of show you. This is actually parafilm. I might have showed you before. It's just kind of handy to try to kind of seal it up because watch glasses with that gap right there. And so, in working problems with this sort of working chemistry problems in this area, it's all about the headspace. So sometimes students and myself too, I'm like, oh well, but you have to ignore that. And as we're talking about vapor, we're talking about that and the headspace of it. I'm going to seal this up. And I don't have my little gun here, but I'm kind of thinking this could be, I could let it set a while, but this is colder. It might get 0 Celsius. Okay. This is room temperature, about 24 degrees Celsius. So if I could go ahead and inspect or have a pressure gauge, which one would have, which headspace would the pressure be greatest? This one?
Yes.
Mm-hmm. Why?
Because it's warm temperature, so more fun.
Yep. Listen, I can almost see this little gas particle slowing down. Like this one, they're just slowing down. Like, oh, okay, I think I'll stay a liquid. Not only that, but the ones that are in your gas phase have less kinetic energy.
So the vapor pressure is dependent on temperature but independent of volume.
Yes. Wait, yeah. Yeah, I'm assuming that we let them go ahead and equilibrate, I think. Yeah, and no matter if I had a big beaker of this slurry or a small beaker, it should get to the same vapor pressure. Yeah. So this table actually is more helpful for this. If we go with, what did I say, maybe 0 Celsius and 25 degrees Celsius. 0 Celsius is right here. And somewhere, if you want to, on the slide, you can, but you'd have to look up torr because we don't use much torr. But the way this works is 1 torr is exactly equal to 1 millimeter mercury. Exact, which is kind of nice. So here we're talking for this left one, or for this one up here, this one with the slurry, you're talking 4.6 millimeters mercury versus the other one, room temperature, I don't know which one we're going to go with, you know, versus 22.4 millimeters mercury, equal vapor pressure. And then this kind of shows you, consistent with what we've been talking about, at 100 degrees Celsius, then you're talking about it having an equilibrium vapor pressure equal to the atmosphere, in general, 760 milliliters. All right, another table. This is the table for this week's lab. You're going to use this table, and it's in your notes. So equilibrium vapor pressure on water. So let's talk. When I was getting ready for this lecture, I'm like, I didn't go back through these 2 problems. Let's see what we got. I really think you need to draw a picture. So a picture we shall draw. All right, we're gonna, I think these, for whatever reason, I like to make these in an Erlenmeyer flask. I'm not sure why. Because we can cap the Erlenmeyer flask easier than trying to use parafilm or whatever. And I'm going to go ahead and put a little puddle of water. It's going to be my water. And it says that I'm going to have 0.110 grams of H2O liquid. I'm going to go ahead and show my little stopper up here, the little rubber stopper. And now the volume of that Erlenmeyer flask, you're running 5.35 liters. And it says that I'm going to start out with dry air. I don't think I need to draw that on there. I'm going to go ahead and write my temperature. Temperature is 25 degrees Celsius. So the point with the dry air, do you guys buy this? That, in fact, I think I'll go ahead and draw a few little dots. Since the air is dry before we started, these little dots are my H2O gas particles. Okay. So there's not a question yet, but here's a question. Now, this particular problem, the fact that we're using the word verify, that means that it will happen. Okay? So what this is saying, verify, or what this will happen, what will happen here is that all of that water will evaporate. We're supposed to verify that. Okay. So I'm going to go ahead and just draw some more dots, and I'm going to say will all evaporate. And I got that directly from the problem. It will all evaporate because my problem said it will. Just to verify that it will all evaporate. Alternatively, why wouldn't it all evaporate? What if I'll kind of answer my own question. What if instead of 0.110 grams, what if I had like 50 grams of water down here? Probably not going to all evaporate. Or we're going to end up with a dynamic equilibrium. It's going to have some left. Okay? So verify that it will all evaporate. And when it all evaporates, we're supposed to calculate the partial pressure. Don't let the word partial throw you off. Partial pressure and pressure of. It just means you might have more than one thing in there, more than one gas. That makes it a partial pressure. Calculate the pressure of the water vapor in the flask. So my object is pressure of H2O is equal to question mark. We're going to assume ideal gas behavior. So I'll kind of give you that. Okay, that's like
I was about to smell it again.
good. I thought it was like maybe God in you. So I'll kind of let you in on what's going to happen is we're going to use the ideal gas law. PV is equal to nRT. We do that in Chem 1, at the end of Chem 1. And of course, R we can look up or we know. T we're given, 25 degrees Celsius. Let's see, number of moles. Oh, you think we can get number of moles if all of this is going to evaporate? Yep. And we have volume. So we're almost there, aren't we? Yeah. Oops, sorry. So actually there's two ways to do this, two approaches to do this. The first is actually what we're going to use. Wait, no, the first is we're going to use the second one. Here's the first one. We could go back to that table, you know, those tables where you circle, I don't even know, we might have circled one about 25, 24 degrees Celsius, we have to go 25 degrees Celsius. Circle that. And we say, all right, if it's going to be in kind of that what we call dynamic equilibrium, if you're going to have some liquid water left there, the maximum amount of water vapor you can fit will be that pressure. Whatever is on the table. That would be our pressure, and then we can kind of backtrack. That would be our pressure. We know the volume, we know R, and we know the temperature, and we could come up with the number of moles of water vapor that would be going around in there. But you're like, wait, no, I know it's all going to evaporate. So actually, we're going to do the second one. Oh, sorry, this is the first one. No. Go through partial pressure. I don't know. All the water evaporates. Okay, I'm not sure. Oh, yeah, okay. So we can't just, sorry. The thing that's wrong with my approach, I'm like, hey, you have temperature, we can look up R, we have the volume. You cannot assume that all of this is going to evaporate. Although the problem said it was going to. We can't assume it, okay? So what we're going to do is we are going to calculate how much water vapor can be in here at equilibrium and compare that mass to this mass. And what we're going to find out is that mass is more than this. So there's going to be, there's extra space up here. This won't what we say saturated. Okay. Okay, well, let's just do it. Looks like this. Okay, so we're going to come up with we're going to come up with the partial pressure of H2O. That would be, I'm back to my original thing. We're going to come up with partial pressure of H2O if all of this evaporates using PV equals nRT. Okay, so if we're after P, we rearrange the ideal gas law equation. So we divide both sides by V, and it looks like this. A really common mistake to kind of throw off what we're dividing by here. So the pressure that we're after is equal to nRT over V, or N, we're going to get the number of moles from that 0.110 grams. R we look up, T is 25. But don't forget, we got to convert 25 degrees Celsius to Kelvin. Volume is given. So let's go ahead and do this. Here's to get from the mass of the water, that 0.110 grams of H2O, and I bet you guys know the molar mass of water is 18.02 grams per mole. So if we put 1 mole over 18.02 grams, we're out to 3 big figs. Then the moles, the N you're going to use is this, 0.00610 moles of H2O. It's near N. If you're like me, you always have to look up R. Do you guys remember what R is? It's something. 8, 2, 3, 4, 5. I don't know. I haven't looked that.
I used to before break.
It's
8, 2, 0, 2, 5, 8.
okay. We'll go with that. So the moles we got from the mass of the water. The temperature, don't forget, don't let that bite you in the butt. So we got to use Kelvin when we're working with the ideal gas law equation. So 25 plus 273, we look at 298 Kelvin, and our volume was given is 5.35 liters. Yep, and the value of R, very good, is 0.082058. And with that value, remember R, if you find different values of R, like crazy different values of R, they're probably different units. So with that value of R, the units are liters, atmospheres per mole Kelvin. So we go ahead and in the numerator put our 3 terms, the 0.00610 moles, the value of R, 0.082058 liters, atmospheres per mole Kelvin. The temperature in Kelvin scale was at 298 Kelvin. Divide by volume, which was our 5.35 liters. And then my favorite part of working with the ideal gas law equation is canceling units. So our moles cancel, our Kelvins cancel, units of liters in the numerator cancel with the units of liters in the denominator, and we have atmospheres. You'll probably tell me 3 sig figs. So you're looking at the partial pressure of H2O, so a little subscript H2O here. Partial pressure of H2O is 0.0279 atmospheres. And what I kind of butchered was a few slides ago, this strategy now will be, we can compare this partial pressure with whatever pressure we see on that table at 25 degrees Celsius. And if this falls short, that means that's all going to evaporate. If this is too big, this is too much for the pressure on the table, guess what? It's not going to all evaporate because it's like a max. That table is like a max. So there you go. So if we look it up, one more thing. On the table is in units of torr or millimeters of mercury. So we're going to have to convert this unit to millimeters of mercury. And remember the relationship is 760. So it's exact relationship. 1 atmosphere is exactly equal to 760 millimeters of mercury. There's no uncertainty brought by the 760 or the 1. So 3 sig figs you're looking at 21.2 millimeters of mercury. Yeah, and so yeah, if you flip back, you find the 25 degrees Celsius, that should say 23.8 millimeters of mercury. So the fact that this fell short confirmed that you had more room for even more to evaporate.
So what's the range, like, maybe you can say, like, events more.
Oh, like if this had been like 23.7 or something?
I mean, like, what if it was like 20, millimeters of mercury? Was it like still close to, like, would it like still be considered close to 20?
If it was what? 20? So 20 is farther away than 21.2.
Yeah, that's what I'm like. What's like?
Yeah, I think I know your question. Well, therein lies a class problem versus a real problem, like in real life, you know, and it depends upon what tolerance, if it's a real life scenario, what tolerance you're willing to accept. So if it's a class sort of problem, you just go by the numbers. You say, hey, since this is smaller, then I know it's going to all evaporate. But in real life, I think you bring up a good point. It's like, I can't live with this. I think this is too close. Yeah. Yep. Kind of an application. Yeah. So since the pressure exerted by all that entire 0.110 grams of water, when it evaporates, it's still under equal vapor pressure. Yeah, it will all evaporate. So we have confirmed or verified that's all going to evaporate. So we're going to do one more problem, and we're going to have to do the other approach. Let's see what our other problem is. These are kind of fun. I hope you guys have them doing homework. Oh no, Mrs. Snipes thinks they're fun. I can't do that. Okay. So let's change this up a little bit. We'll still use an Erlenmeyer flask. See what we need to change though. The water, we're jacking it up a little bit. 1.25 grams. This is an entirely different problem though. 1.25 grams, but it's similar in that we had dry air. We're going to let it kind of evaporate. The volume is not 5.35. The volume is 9.70 liters. Temperature is warmer. And don't forget, we've talked in Chem 1 that that's not a mistake. Like when we put the decimal there, after the 40, that gives you 2 sig figs. So here's the question then. We're supposed to verify. Again, verify means that it will happen. Verify, it means it won't happen, that not all of the water will evaporate. I'm going to say not all will evaporate. Okay. So we're supposed to confirm that. And again, assume ideal gas behavior. So PV equals nRT is 1. Okay, so that's not what we're after now. So instead of, now, to me, this isn't helpful. Sometimes this problem goes like this. Question mark. Will there be the H2O liquid left? In other words, verify that there will be an H2O liquid left. Sometimes I start to say, the question is how much H2O liquid will be left? And when we answer the question, we're going to be really close to answering that question too. So here's our 2 approaches. See if this will make sense. There are 2 approaches. We did the first approach last time. This time we're going to do this approach. So let's go down to the second bullet. If we go ahead and use the table to find out what the equilibrium pressure is at 40 degrees, we can go ahead and pull off the equilibrium vapor pressure at 40 degrees Celsius. We have a volume. We can go ahead and come up with the number of moles of water at equilibrium that will be floating around here. After that, we can take the moles, N, and we're really close to getting grams. So here's the deal then, is if our grams is less than 1.25, which it will be, okay, the grams of water floating around in this vapor phase, we said that not all of the 1.25 will evaporate, then we know that there was some liquid left. So that's it. All right, so it looks like this. Okay. So in this case, we are going to solve for N. So rearranging, dividing both sides by RT. N is equal to PV over RT. So this is going to be the number of moles of water vapor that will be evaporated at that volume at that temperature. So if you look up back to the same table we've been looking at, if you jack up the temperature, of course you're going to jack up the equilibrium vapor pressure of water. So from the table, you're looking at 55.3 millimeters of mercury. So that is actually going to be our pressure. That's P. 55.3 millimeters of mercury. That's going to be our pressure in the ideal gas law equation. But with the value of R we're using, we got to convert it to atmospheres. We can do that. So remember 760 is the link between millimeters of mercury and atmospheres. So if we make our first term the 55.3 millimeters of mercury and make our second term 1 atmosphere over 760 millimeters of mercury, so units of millimeters of mercury cancel out, we're looking at units of atmospheres, 3 sig figs, and you're looking at 0.0728 atmospheres. So remember, that is the equilibrium vapor pressure. That's like the maximum vapor pressure that you will have at that temperature in that container. So we're going to plug that as pressure into our PV equals nRT. Of course, we already had the temperature and volume. So the temperature, we better make sure is in units of Kelvin. So we're going to take our 40 with uncertainty begins at the ones place. Add 273 units to it, get 313 Kelvin, and our volume is given. So we're ready to plug into, find the number of moles of water that would be in that container at that temperature at equilibrium. So in the numerator, we have 2 terms, that 0.0728 atmospheres times 9.70 liters. In the denominator, we have our ideal gas law constant, 0.082058. Units of R are liters, atmospheres per mole Kelvin. Then also in the denominator is our temperature, which says 313 Kelvin. Looks like we're allowed 3 sig figs. So the number of moles of H2O at equilibrium, given that volume and that temperature, is going to be 0.0275 moles of H2O. So we can't really compare the moles directly to our grams. We're going to have to convert moles to grams and then compare. So here we go. What's the mole mass of water? 18.02 grams per mole. Got it. So if we take that 0.0275 moles of H2O, use what you told me, 18.02 grams of H2O per 1 mole of H2O. Rounded to 3 sig figs, that means the mass of the water in its vapor phase is 0.495 grams of H2O, which we have done it then. We have verified that of the 1.25 grams that you start with of liquid, only 0.495 grams are going to be able to evaporate. So like I said, a kind of a follow-up question might be this one you see at the bottom. So what will be the mass of the liquid at the bottom? Well, you could just say we started with 1.25 grams. From that we subtract 0.495 grams, which is the water in its vapor phase. And remember, since we're subtracting, we can only go with decimals here, so we can only round to 2 decimals instead of 3, so you're looking at 0.75 grams. So these are the kind, and there's definitely in this unit and another unit in Chem 2 where there's definitely different ways to work the problem. So, and this says that, you know, we've been talking about these little particles are water particles because, well, I guess, but you know that there's nitrogen particles and oxygen particles in there too. It said it was dry. It didn't say it was a vacuum. So my point is I could get a different color and do different color dots, and the nitrogen and the oxygen that's also in there, they do their own thing. They all kind of independent of each other to some extent. Well, when it comes to equilibrium pressure. All right. So there you go. So we do on Wednesday. Great about that. I was hoping, I was thinking about the roads and how do I want them to do the roads? I want to take a squeegee and go down get all the water off, and then when it freezes. You like isopropanol?
I really like